All right, guys, we're doing the winter paper of 2014, paper 31. Let's jump straight in. All right, guys, this is just a quick question about just sort of your interpretation of distance versus time graphs and so on and so forth. You basically just need to match these two up. Okay, so it's distance on the top, time on the bottom. Okay, so let's go in reverse order. So if we look at C, it's nice and flat, so it's got no gradient. Therefore, if the distance is staying the same no matter what time we look at, it is stationary. All right. And we got B. Okay, its gradient is a constant. The gradient over here is the same as the gradient over there. So if the gradient is the same, it's moving at a constant speed. All right. And here we have one that is accelerating. The gradient is lower here and then higher here. So increasing speed. This is the same one, same sort of question, but instead of it being distance on the top, it's now speed, right? So we look, this has got a flat gradient, so its speed is now constant. So constant speed. Then we've got E, which is like a constant gradient. So now instead of the speed being constant, the acceleration is constant. Okay, and then we have one where the gradient is increasing, number D, so it's increasing acceleration. All right. It's just got to do with some potential energy and acceleration things. Just very briefly asking you to calculate the average acceleration. So we know the speed goes from 0 to 10.5 meters per second in 1.5 seconds. So we just say 10.5 minus 0 all divided by 1.5. And then it says at one point she reaches her maximum speed. State her acceleration at this point. Well, if she's reached her maximum speed, that means there is no more acceleration of any form. So the acceleration would just be 0. What can be said about the forces acting on at this point? So we know from Newton's third law that force is equal to mass times acceleration. The key word is net force. Or sorry, net force times mass equals mass times acceleration. Since the acceleration is 0, the net force is 0. So basically the forces are in equilibrium. So the force acting upwards and the forces acting downwards are basically equal. All right, some more potential energy questions about a diver diving into a pool. Calculate the increase in gravitational potential energy of the diver when he climbs up the platform. All right, so obviously as he's climbing, he's increasing his potential energy. Okay, we just use mgh. We've got his mass. We know the height of the platform. And g we can approximate to, let's say, either 10 or 9.81 if you're being fancy. And you can then approximate his, calculate his increase in potential energy. Then we can calculate the speed. Then you're asked to calculate the speed at which the diver hits the surface of the water, ignoring any effects of air resistance, as this would also, this would decrease the energy and be more harder to calculate then. Basically, we just equate the gravitational potential energy here to the kinetic energy, and we can just stick this into these equations. I mean, we've already actually calculated this in the previous question, so we can just equate it to this. But notice that if you weren't given the mass of the diver, you could actually calculate the speed with just the height, and taking a guess again, like approximating that to 10. Approximating g, and you wouldn't actually need the mass. So there are some questions that sort of are formulated in that way. So you don't necessarily always need the mass. All right. In another dive from the platform, the diver performs a somersault. So he spins and rotates. He straightens and enters the water at the same as shown in this figure. So sort of straight and flat. And then they ask, is there any difference to the if at all, to the speed calculated? And at a first glance, you would say no, because basically, because he's falling from the same height, it wouldn't be any different. And that is the answer, because even though he's rotating, when he leaves the platform, he falls through the same height, so therefore has the same amount of loses the same amount of potential energy into the form of kinetic energy, and therefore hits the water at the same sort of speed. In this scenario, because we are again ignoring air resistance, this works out. But I would imagine if there were to be air resistance involved, he would be slower, because as he's falling in, let's say, a flat form like that, as he's rotating, if he's rotating about this, he might have more air resistance, so it might actually change the overall speed in that case. But because we're ignoring air resistance, and even though he adds a bit of energy, he's got sort of a form of rotational energy, it doesn't really affect the speed at which he hits the water. All right, this is just sort of how a question trying to illustrate how sort of atmospheric pressure presses on the can. So basically, initially the pressure on the inside and the outside of this can are the same. Then you reduce the pressure on the inside of the can to 600 pascals, 6,000 pascals, and then the can sort of collapses in on itself. And it says, so why does the can collapse in on itself? Because then it's not in balance anymore. There's a net force then on the walls of the can. So if we say, like, if this force is now the outside pressure and this is the inside pressure, there's now a net resultant force. Then they ask you to calculate that net resultant force, and we know that it's pressure times by area, and we just need the difference in the pressures in this case, and times it by the area, and we should get then the net resultant force that crushes the can. All right, this question just talks about like mercury being sort of basically these two sort of columns of water are stacked on top of a mercury bend, and you can see the sort of in this case, the levels are equal, they're at the same height. So what condition must be true for this to be at the same height? Basically, the pressure pushing down here, sorry, let me draw that in, pressure pushing down here and the pressure pushing down here must be equal, because if they weren't, otherwise the mercury would either rise up on one side until at that height the pressures were balanced again. But since these are at equal heights, the pressure from here is equal to the pressure induced here. And then you needed to calculate the density of the oil. So since we knew sort of the height, we know the height of the water here, right? And we know the density of the water. We can then compare, and we know the height of the oil here. We just use our rho GH equation to then compare the two densities. So we're going to know that roughly we can already see that the density of the oil is going to be less. So we just equate these, and let's give this, like, let's say it's oil, and let's say this is water, and this is for oil, and say this height is for the water, and we can cancel out the g's, and then we just rearrange this, and then we can get the height of the density of the oil, and we can stick this on that side. All right, quite straightforward. Okay, this is just a question about how you would go about calculating the specific heat capacity of a thermal mass. And we've got the whole sort of set out. So this is our block of aluminium. We've got the heat air element here that's just going to add heat into the block, and then we've got basically a thermometer over here, and then just asks you to outline like how you would go about this. And basically, what sort of quantities you would need to measure to go about this. So we basically need to figure out how much power is being put into here. And in order to get power, so we would need, like, let's say the power is equal to the current times by the voltage. So we would need current and voltage. But we also want to know then eventually the net amount of energy going in. So we need power, and we need to, times that by time. So we'd also need some sort of stopwatch to measure time. And then we obviously have to measure the change in temperature. Let's just use the symbol for temperature. Sorry, it's a bit messy. And we need to know the mass of the block itself. All right. So we need all these guys. We need to be able to measure all of these to get the thing. Then they just ask you, to sort of formulate an equation to calculate this, and you just equate the electrical energy going into the thermal energy, basically conservation of energy. So we know that, okay, the energy going in is the voltage times by the current times by the time. So that's the amount of energy going in. And that equals a specific heat capacity and mass times by the change in temperature. And you can just rearrange this for C. All right. So then another student used an experiment without using insulation. He obtains a higher value for C. Explain why the student measurement leads to this higher value. Basically, we get heat loss. So basically, when we make this assumption of it, this assumption there is sort of less valid. Even though even with insulation, there's probably still a small amount of heat loss. But if this insulation is good, this sort of holds true. But the problem is the minute you sort of remove this insulation, you get a lot of sort of, you get all your different heat losses. So you get your convective, if it's sitting on something, some form of conductive heat loss, and also your radiative heat loss as well. So basically you need to pump in more energy to get the same temperature change. And this, if you just were to use this equation, would be inaccurate, and you would obtain, like, you'd be putting in more energy. So you would think that the capacity is higher. All right. This just talks about, this is basically, this question is trying to sort of like question the learner about longitudinal and transverse waves. I mean, basically, when we talk about longitudinal waves, the movement of like the particle, let's say, or the medium is in the direction of the travel of the wave, sort of like forward and backwards. In transverse, it's perpendicular to the direction of travel. Then I just wanted some other examples. So another example of a longitudinal wave would be sound. It's your sort of main obvious example. And then let's say for a transverse wave, could either be vibrations on a string, transverse vibrations on a string, or could be electromagnetic radiation. And then it just wants you to plug in, speed and frequency to calculate wavelength. And you just need to plug that into the formula for it. This is just to do with sound needing to travel in a medium. Basically, you have like a bell sitting inside of a vacuum chamber, and if you took the air out of the chamber, would you still hear the bell? Well, if you took all of it out, you wouldn't, because sound needs a medium to transfer in. However, let's say if this was a light inside, so electromagnetic radiation doesn't need a medium to transfer in. All right, this is just we're just going to skip straight past this one. You just had to draw in some lines. It just was about like reflection, and you just needed to sort of like, draw in some reflection lines. A bit boring. All right, the circular wave fronts. Okay, so basically you just have this sort of point source, and it's emanating these waves. These waves are sort of reflected off this barrier. And then it sort of says the wave fronts seem to come from a single point. And basically it sort of behaves as if there was another source sitting over here emitting the same sort of waves at the same amplitude and frequency from this side, if there's obviously no loss in this barrier. So you could just draw a point on this side, and then you could just sort of like show that, these sort of, this is a terrible drawing, came round from this side as if they were emitted from this source there. All right, a small cylinder of compressed helium gas is used to inflate balloons for a celebration. In the box below, sketch the diagram to represent the arrangement of the helium molecules in the balloon. And it's sort of, there is no real arrangement. It's a sort of randomized. And if you want, you can draw in some vectors for motion to show that, some are fast, for example, like this one moving in this direction, and that's sort of randomly moving in another direction, a slightly slower speed, and maybe another fast one in, and so on and so forth. And you're just trying to bring across to the marker that you understand that sort of gas behaves in this sort of like random motion sort of pattern with no particular structure to it. And then it wants you to then compare this between, let's say, a solid. And a solid, it would be, you know, everything would be organized, and everything would be sort of in a depending on the type of solid, but would be in like either some crystal form where everything is sort of locked in place. And it wants you to then talk about like sort of the forces acting on it between like so the forces, you know, holding these together are really weak. So they sort of broken out of these bonds and can move around, where in a solid, they're sort of locked in place. All right. Then you've got some typical PV equals a constant calculations. So they say that the helium in a cylinder has a volume of this much and is at a pressure of this much. Then the pressure of the helium in each balloon. So we know like the change in pressure. So we can look for the change in, so we can figure out how much, you know, how much volume of helium if we used up these, you know, the entire cylinder. And then we know the volume of each balloon. So we just basically use PV equals a constant, right? Which is equal to, let's say, we can say cylinder, balloon, right? So we know this side, we know this, so we can then get that. So then we can get the volume of all that gas. Well, balloon, maybe it's not, it's slightly misleading, of, let's say, the cylinder, let's call this balloon pressure. And then let's call this, like, I don't know, balloon cylinder. In other words, the volume that of that gas that would be taken up if the cylinder was all released to balloon levels of pressure. And then we basically then just take this guy here and then divide it by the volume of each balloon. And let's just call this balloon on its own. So, and then you would get how many balloons it would create, or how many you would be able to inflate. Later, the temperature increases and some of the balloons burst. Suggest and explain why this happens. So if the temperature is increasing, the pressure is increasing with it, and eventually the pressure inside the balloons is just so strong that it just rips through the material, because it's continuously stretching the material and putting more load on the material of the balloon, like the rubber that's the balloons are made out of, or maybe it's silicone. But anyway, eventually the balloons would just tear and burst because of the increase in pressure. All right, this is just some basic sort of questions on you know, a typical charger that, you know, you would charge your cell phone with. And basically it's asking you know, what component converts the charger that converts the AC to DC. And well, whenever we have AC to DC, there's always one component in mind, and it's just a full wave rectifier or bridge rectifier, lots of different names for it. And then they want to know, you know, what's the quantity that has the value of 50 hertz. Or the input has the 50 hertz. So it's basically, you know, the wall, the input from the wall. So the grid. So it's basically saying it's you know, that you would plug this into a wall that, you know, a wall socket that had 50 hertz, which is your sort of standard in the UK. In other parts of the world, it could be 60 hertz. All right, calculate the output power of the charger. So we just say, well, the output power is current times by voltage. It's quite simple, just times the two together. Then it says the energy transferred in the input circuit when the cell phone is charged for about 1.5 hours. So you just take the power and you times it by the time, and just to make sure that you convert like hours into seconds. Okay. in the following list, underline the quantity that is stored in the battery of the cell phone. Well, we're storing energy. You don't store power. Power is a transferred thing. Current is also a transfer thing. And voltage is sort of potential power, potential energy in a sense. But no, what we store in the battery is energy. All right, so this is just a question on radiation. It says the technician sets up a radiation detector at a university laboratory for use in some experiments. Even before the radioactive source from the experiment is brought out into the laboratory, the detector registers a low count rate. So it's sort of picking up something even though there's no radioactive, the radioactive source isn't there. But there is background radiation because there's a still slight level of, there's gamma rays from space and other sources of radioactive particles, and they have sort of a low amount, but a detectable low amount of background radiation. A radioactive source emits alpha particles, is placed on the laboratory bench, and the source is gradually moved closer to the detector. At first, the detector registers a low count rate, something slightly less than the count rate registers without the source. The count rate suddenly increases to a very high value when the source is very close to the detector. Basically, what happens is the detector is sitting there and it's picking up background radiation, which fluctuates somewhat. So it can drop a little bit lower for a couple of seconds, come a little bit higher. I mean, its average sits quite constant, but momentarily it can fluctuate. And then as the source gets closer, you actually then start picking up the alpha particles. And basically, this is because the alpha particles, because they're so big and heavy, have a very sort of have a quite a short distance over which they can be detectors, because the minute they start banging into the air around them, they slow down and will then not then be detected by the detector. And then in a second experiment, alpha particles pass between two parallel horizontal metal plates in a vacuum. They then continue to the detector. So initially they just go sort of straight through. Then they say you apply a positive charge on the upper plate and a negative charge on the lower plate. And then it says, well, sketch the new path of the particles. Basically, they just sort of turn off and sort of divert towards, curve towards the metal plates. The bottom metal plates. And this is because this has a negative charge, and alpha particles have a positive charge, and positive is attracted towards negative. And then state what happens to the count rate by the detector. Well, it must either reduce somewhat, or reduce all the way down to the background level, depending on how strong this charge is and how close the sources. But basically, the overall answer is reduce to background levels. All right. In a room, there are 4 electric lamps in parallel. All right, that's the key word. With each other controlled by a single switch. With all the lamps working, one of the lamp filaments suddenly breaks. What, if anything, happens to the remaining lamps? Explain your answer. So the keyword is in parallel here. So when something's in parallel, it's getting the same voltage supplied to it. So, and the fact that it's in parallel means that if one of the lamps breaks, there's still going to be, it will still receive, it'll still have the rest of them will still have a completed circuit. So since the voltage is staying the same and they still have a completed circuit, they shouldn't dim in any way. They should just be all bright, and they should stay the same amount. All right. This is just illustrating how two-way switches can work. So you've got your switches over here. It asks you to sort of, fill out this diagram. Basically, when you just need to take a look at this diagram, see which ones give you a completed circuit. So if, let's say, this one is in this position, but this one is in this position, so this is broken, then this would not be a completed circuit, and vice versa. So you just go through the process. So 1 and 1 is a completed circuit, so it would be on. 1 and 2 would be off. 2 and 1 would be off. 2 and 2 would be back on again. You just fill that out. Explain why this arrangement of the switches is useful. It's very useful because no matter what position the other side is on, if I just alternate this, I can change the state of this and vice versa. So you can have one switch, one of these downstairs, one of these upstairs, and you can just sort of click between the two until you get sort of the state you want. So you only need to operate one of these for this to change the state of this guy. All right, name the process that causes potential difference across a solenoid due to the movement of a nearby magnet. That's just basically electromagnetic induction, quite straightforward. Shows, so then you got this diagram over here, and they say, okay, we're going to push a magnet through it. Then in this question, describe the movement of the pointer over here. So what happens is, once it starts moving through, this will deflect depending on which way this is set up. It'll deflect one way, and then as you slow down and then stop, it'll return back to 0. Now they say the magnet is pulled in the opposite direction at a higher speed, so to the left at a higher speed. So these are the key things. Always good to underline your stuff when you're working through. Underline the key points from questions. Compare the movement of the pointer with this case. Basically, because it's going, first of all, it's moving the other way. It's going to the dial will deflect in the opposite direction that it originally deflected, and should then, because it's moved quicker, moved at a higher speed, the deflection should be greater. And because it's also moved quicker, like through this thing faster, the length of time it is deflected will be reduced. And that's the end of that paper. Thanks very much, guys. See you soon.